Okay, so today the topic of discussion is how to model and solve an optimization problem. So I've never given this lecture before because nobody ever asked me to give this lecture before. I've prepared something, but it's going to be an interactive lecture, so feel free to ask as many questions as you want. And hopefully I'll be able to give a better lecture in the next year when I'm teaching this class. So whenever you think about optimization problems, so I'm taking the point of view of an entrepreneur as well, because I run a company and I've worked on a lot of consulting assignments with industry, and I've also solved a lot of optimization problems as part of being a faculty with my students. So I've had a very broad type of inputs. So what is day one of an optimization? What does day one of an optimization looks like? So as a university faculty, you kind of know what the optimization problem is and you get into the weeds. But because most of you are not going to become a faculty, you are all going to go to industry, I want to give you a glimpse of what happens on the first day in industry and how that problem percolates down to an optimization problem that you will then get an opportunity to solve as an optimizer within the company. So on day one of the company, the CEO has a dream because the CEO goes around, talks to 500 people. So the CEO has a dream and it's a problem that everybody is talking about, everybody agrees on that it is a problem. So the problem could be, so I'm going to give you a problem and I want you to name a company which basically tries to solve that problem. So we want a reusable rocket. SpaceX, okay? We want cheapest items at your doorstep. Amazon. So we all agree that that's a problem. We want lots of movies in one place. Movies, TV series, Netflix. We want robots in Warzone. Military. Boston Dynamics. Yeah. Okay, so these are all the problems that everybody agrees on. Everybody knows that this is a problem. This problem needs to be solved. Okay, so the CEO goes and tells the VP of engineering, John, we need a reusable rocket. Okay. And so it's VP of engineering's problem to come up with a functional and non-functional requirements for this problem. So what are functional requirements? So what are functional requirements for a reusable launch vehicle? So this would basically talk about the quality, performance, security, etc. about the product. So I think I'll write a few of these functional requirements for a reusable launch vehicle. So first one is it should come back to launch pad. I think it's a very reasonable requirement because we want a reusable launch vehicle. So that's definitely should be the case. It should come back to the launch pad. The second requirement is should blow up using a button. So if we see that the rocket is malfunctioning and it's going towards an area where humans live or where there is some civilization, then we should be able to blow up the rocket in the space itself. It shouldn't come back to the Earth. So that's also an important requirement for a rocket. Then it should maneuver at high speed. Does anyone know at what speed rockets move around in the space? Any idea?
In the low Earth orbit, like 17,000 miles per hour.
Yeah, but that's low Earth orbit. So this is a reusable rocket, so it needs to go to like 100 kilometers and then come back. 100, 200 kilometers and then it will come back to the Earth. So it generally travels around Mach 6 to Mach 10. And this is the time when my aerospace engineering skills comes to work. So, after Mach 1, there is a discontinuity in the flow field. So the way the fluid works, there is a discontinuity in the field, in the velocity of the fluid, which is air in this case, and as a result of which controlling at this particular Mach is extremely difficult. You have to have very sophisticated controllers to be able to control. So actuators are very sophisticated when you want to control at this particular Mach. That's why airlines, passenger airlines would fly at Mach 0.8 to 0.9. So they don't want to get into that complicated region. But fighter jets would fly at Mach 2 to Mach 3, and then these rockets generally fly at Mach 6 to Mach 10. What else should be a functional requirement? Carry a payload of 2,000 pounds. Fourth is already done. Fifth, any other functional requirement? Withstand (1000°C). That's because when you are traveling at this particular speed, the temperature right after the discontinuity in the flow field will have a very high temperature, roughly of the order of 1000°C. So the outer shell of the rocket is coated with ceramics in order to make sure that the entire rocket is safe from this particular temperature. Otherwise, the metal will start melting at that temperature. And then you need to have a landing gear. But note that the landing gear is going to be used only when the rocket is empty. So the payload is in the space and the fuel is almost burnt out. Okay, so it doesn't have to have a landing gear. So if you think about an aircraft's landing gear has to work at the time of launch and at the time of going up and at the time of landing. So the landing gear pretty much has to take the entire weight of the aircraft. On the other hand, for rockets, it doesn't have to take the entire weight of the rocket. It only has to work at the time it's coming back, and at that time the weight is much, much lower. So the landing gear has to be optimized for the return weight of the rocket. Okay, so these are the functional requirements. There will be non-functional requirements as well. So we'll get into it in a bit. Non-functional requirements typically talks about the architecture of the whole system. Now, of course, we are concerned mainly with the optimization part here. So which of these functional requirements requires an optimization algorithm? Yeah.
The first one?
The first one, right? So why should this be an optimization problem?
Because directly related to per path and stuff like that.
Right. So it should, basically this should come back to the launch pad is very similar to the tracking problem that we have talked about. So when I say it should come back to the launch pad, of course, it means that we only have a terminal cost, we don't have any running cost. But typically problems of this type, you also have to have a running cost because you want to make sure that the entire rocket is moving in a reasonable, along a reasonable trajectory, which consumes the minimum amount of fuel. So there will be individual teams. So under VP of engineering, there will be a team that works on the trajectory planning, which is what this particular part comes under. And the trajectory planning will have a lot of optimization people. Should blow up using a button. I think this is more for an explosive. There will be one particular team which will be working on explosive for rockets. Maneuver at high speed, there will be a hardware team which will figure out how to create that control surface in order to be able to maneuver at high speed. And there will be one team which will talk about how to carry the payload, how should the payload integrate into the rocket, and how should it detach from the rocket. There will be some material science people who will be working on this part, and then there will be some people who are working on this part. So every part will have a big team working on that particular part. So we are only concerned with this part because we are optimization people. So we should look at how to create this algorithm which can take the rocket from ground to 200 kilometers, and then it will take it back from 200 kilometers back to Earth. So then somebody within the optimization team will come up with non-functional requirements. So non-functional requirements I think the first, I'm just going to make things up. Optimization solver must terminate in 100 milliseconds. So every time we want to optimize when we are doing the tracking, so there will be one optimization that will be done at the ground station. How many of you have seen this movie Hidden Figures? How many of you have seen? You have seen the movie Hidden Figures? No? Okay, you guys have to go and see the Hidden Figures movie. So what happens in Hidden Figures movie is there is a lady who figures out what the trajectory of the Apollo mission should be, like how should the aircraft go from Earth all the way to moon. And actually her main job was not to figure out how to go to the moon, but if in case something wrong happens, how to come back safely to Earth. So that was her job. Okay, so she came up with various methods to figure out how to go back to the moon, and if in case something wrong happens, how to come back to the Earth. Where exactly should the spacecraft land? How should we retrieve those people and get them back to safe location? So all of that stuff is something that she worked on. So it's a great movie. I think you should watch it. It'll teach you a thing or two about optimization as well. Okay. So now the problem is that that lady gave us, this is the trajectory, this is how we are going to go. Now some optimization guy has to sit down and say, okay, every 100 milliseconds, I'm going to optimize the trajectory, I'm going to do the tracking, I'm going to run the tracking algorithm, and I'm going to make sure that the output of the optimization solver comes in 100 milliseconds. So in this class, we have not talked at all about the execution time. We have not made any attempt to force you to think about the execution time and the memory complexity of the optimization algorithms that you were implementing. So many of you have used maybe 500 variables and may have stored many, many matrices. But when you are putting it in hardware, you really have to think about what the memory complexity should be and what the time complexity should be of running the optimization. So some person in the optimization team will say, okay, the optimization must terminate in 100 milliseconds on microcontroller. So the hardware will also be specified, X taking in data from Y. Because all the sensor data is going to come and it will sit on the some memory location within that microcontroller, and the microcontroller will have a CPU, and that CPU will be running all the optimization, taking in data from all the different sensors across the rocket. And then whatever output comes out, whatever is the control output that comes out of the solving of this optimization problem, that needs to then communicate to the actuator to implement. And so these people will take that as input, and then they will implement that control input to the actuator, and then hopefully the rocket will maneuver in the right direction. Now this particular thing is done. So this one is something that a VP of engineering will do, and then this is something that a director of engineering would do. So it's still a managerial position. Now the director of engineering goes to the senior engineer and junior engineer. So whenever you go out, you will basically work as a junior engineer or as a senior engineer in appropriate companies. So you get this, you see this as your requirement. Okay. So from this requirement, now you need to write an algorithm on this microcontroller X, getting data from Y. So you need to write all the code and write the optimization algorithm that terminates in 100 milliseconds. Now the problem is, so let's move away from tracking problem. So far we were talking about tracking problem, but let's think that we just need to do some optimization. So if you are in Netflix, you will be asked, what do you think is one of the functional requirements that requires optimization in Netflix? What is it that Netflix wants to optimize? Yeah.
Watch time?
Not quite the watch time. See, watch time depends on you, like whether you are, if you are cooking and you cook in 30 minutes, then you will only watch for 30 minutes. I don't know, that's what my algorithm is. But I'm sure everybody has different algorithm for watch time.
Yeah, the recommendation.
Discovery. So they want to optimize discovery. So they want that as soon as you get onto the Netflix app, you should be able to find what you need to watch within the next, I don't know, 5 or 6 clicks. That's That's what they want to optimize. What do you think Amazon wants to optimize?
Also discovery of something.
Discovery of products. But do you think that there is some nuance in Amazon's objective in comparison to Netflix's objective?
They want to get things to you as fast and cheap as possible.
Fast and cheap is definitely one of the things, but so I think it's somewhat non-intuitive, but on e-commerce websites, the goal is not to optimize the number of clicks to be as small as possible. It is to be around 30. Like, they want you to explore like 10 items and pick one of the items to purchase. Okay, so that 10 items is very important. Like 6 or 7 items, I think, is a sweet spot. If you see 15 items on Amazon, then you will go into analysis paralysis and you won't buy anything. That's what happens. If you buy if you see 2 items on Amazon and buy one, then you will always have a regret in mind that maybe if I had looked more, I would have found a better thing. So 6 or 7 is kind of the sweet spot. So roughly that comes around 30 clicks. So you go to a item, and then you go back to the main page, search page, and then you go look at another item, then you go back to the search page. So you do this like there are 30 or so clicks, after which you are satisfied that whatever you are getting is the best deal possible, and then you will go ahead and make that purchase. So in the Amazon's case, they want to get to 30 clicks as soon as possible. What other thing? Boston Dynamics. What do you think Boston Dynamics requirement is? Any idea? So the reason why Boston Dynamics started was landmines. Finding landmines was a very difficult problem. It could cause death of the people who are finding landmines. So the goal for Boston Dynamics was to find landmine as soon as possible. Okay, so that's what their robots were built for. And of course, now they have expanded into multiple other things. So now they can fight, they can get into a room, and they can find terrorists and so on and so forth. Like Boston Dynamics can do a lot of cool things now. I mean, I think they've also started dancing. Like they can also entertain people in a restaurant eating food. So I guess that's a new functional requirement for them. Has anyone seen the Boston Dynamics dance video for their robots? Okay, some people have seen it. It's on YouTube. It's pretty famous. Okay, so those are the functional requirements, and all of them percolate into some optimization problem that needs to be solved. Now, there are 2 types of optimization, as we have seen in this class. There is a static optimization, and then there is a dynamic optimization. Okay. So when do you use static optimization? So typically static optimizations are optimizing steady state behavior of something. Okay. So it's always steady state. I mean, not always. Okay. Most of the time, the static optimization could be coming from a machine learning problem like a classification problem or a regression problem or a dimensionality reduction problem, or the static optimization could be coming from a steady state behavior of a system. So one example could be, for instance, Kroger discount. So if you go to Kroger, you will see that every week they put something on discount, like 10% off, 15% off, 50% off, whatever. Right? So they keep that particular discount for a week. That's a steady state optimization. So they expect, if I keep these discounts, these are the number of items that will sell, and so that will optimize my profit or optimize my loss or whatever that may be. So they figure out what the discount should be in order to maximize their profit or minimize their loss. Okay? So you can treat it as a static optimization problem. Now, of course, you could come back and say, oh, I can make it dynamic. Like you come in front of the item, and then the display will look at your face, look at your clothes you are wearing, and then it will tell you, okay, your price is X. Okay, but that does not happen because there will be some person who says, well, the price has to be the same for all the people. It cannot be differential pricing. Although airlines do they used to do differential pricing. I think they have stopped doing differential pricing, but at some point of time, airlines used to do differential pricing. So anyway, some people said, okay, there should not be any differential pricing. it should be the same price. So then Kroger discount becomes a static optimization problem. You need to find what the sale percentage should be. Should it be 10? Should it be 15? Should it be 20? So as to minimize the loss or maximize the profit. In the wireless system, so we all communicate through phones. I don't know much about wireless systems, so I'm just pulling some stories out of the hat. So whenever it rains, whenever it's humid weather outside, or whenever it's snowing, the electromagnetic characteristics of the electromagnetic wave propagation characteristics of the air changes quite significantly because of the rain. So then you need to figure out, you need to tune certain things at the base station in order to make sure that you are communicating without any error, even while it is raining, right? So that automatic tuning happens, but that again happens through a static, like you can make it dynamic. I think most of the people are moving towards dynamic optimization now, but until now people were mainly looking at solving it as a static problem, wherein somebody will look at the weather in the morning and then it will say, okay, this is what the gain number should be for that particular system. So those are sort of steady state behavior. You want to optimize the steady state behavior, and therefore you pose it as a static optimization problem. And then you need to know three things. The first is, what are the design variables? This is your X. What are the parameters? This is your theta. What's the constraint? And the fourth one is objective. So what's the function f? And this is h and g. So what are the equality constraints? What are the inequality constraints? What's the objective function f? So the parameters theta is something that you need that information upfront, and then you optimize the function f of theta. Let me just put theta here as a subscript. So what you do is you minimize f of theta subject to h of theta equal to 0, g of theta less than equal to 0. You find the value of x, and then you implement that x in the system. Okay, that's a static optimization. That's how the static optimization problem comes into picture. Now suppose there is a possibility, because of some new technology, because of some new development. Let me give you another example. So if you were building a dishwasher in 1950s, okay, the dishwasher weren't very sophisticated at that point of time. So there are a lot of PID controllers in dishwasher to figure out how the motor is going to work and how should it be cleaning and how much pressure it should be sending to the water and all that stuff. So that's the design variable, like what is the torque of the motor, right? That's the design variable. So what they would do is, the torque is actually controlled by some gains. So there is a P gain, and then there is an I gain, and then there is a D gain, right? So there are three gains. So they will try to figure out what's the best gain for getting the best performance out of that dishwasher. So at the factory, they will view it as a static optimization problem. Some guy is going to sit there and it's going to tune the gain manually every point of time and see whether the dishes are coming out clean or not. And so once they figured out, okay, this is the winning PID controller, so that's the winning X, and then they will create the same replica, make thousands of such dishwasher and sell it to everyone. And since you guys are in graduate housing, I'm sure many of you have seen dishwashers from 1950s in your apartment, hopefully, I don't know. So that's how the dishwashers were created back in 1950s. Now, of course, they are a bit more sophisticated. So this theta, so in my dishwasher, the current apartment that I'm in, the dishwasher has this technology where it senses how much dirty the dishes are, and then it injects exactly the right amount of, what is that called, dishwasher liquid into the water. So there is a parameter theta, and now there is a sensor that senses what the parameter theta is, and then it optimizes X, and then it sends exactly X amount of dishwasher liquid in the thing. So what I'm saying is many a times because of technological evolution, you might see some static optimization being solved, and then later on some other static optimization will appear, and then you will start solving that static optimization problem. Okay, so this is what happens. Now, sometimes when there is a significant technological revolution, then you can start solving dynamic optimization. The thing in dynamic optimization is you need to be able to solve the optimization at a much slower time scale than the actual activity is being performed. So if you're driving a car and it takes you 20 minutes to solve an optimization problem for running the car for 1 minute, 1 second, it's not going to work because you need to solve that optimization at every point of time. But if you can solve 20 minutes of driving time within a second, then it makes perfect sense. It's ripe for dynamic optimization setting. So you have to see there always has to be some technological evolution for you to move from a static optimization to a dynamic optimization. So pre-2005, if you were driving a car, there is only one route to get to the university, and you will always take that route and back because you couldn't see what the traffic is going to be. So that was static optimization. Now, because of Google Maps and because of other maps, we can actually know what the traffic is going to be, and so now I can dynamically change my route because each of these route optimization takes a few milliseconds, right? So the optimization, so not only am I able to observe what the traffic is going to be or traffic is on the road, but I can also solve the optimization problem at a much faster time scale than the execution speed of the dynamic problem. So I can do dynamic optimization now. So whenever you want to solve a dynamic optimization, you have to worry about state, action, model, and then you have to, so this is the system model, this is your FT, this is XT, this is UT. Then you have constraints. Then you have to worry about the cost and the terminal cost. And then you need to worry about hardware. And if you're solving a very complicated dynamic optimization problem, then you have to figure out the function approximating class. For most simple problems, the function approximating class is just tabular, but you can of course pick more complicated function approximating class that we talked about in the previous lecture. And a lot of this basically builds on what the hardware limitations are. If you have severe hardware limitations, you can't really pick complicated function approximating classes. Okay. So what you have to do, so the director of engineering came up with this non-functional requirements and he passed it on to you. Now it's your job to figure out, is it a static optimization? Then you need all of this stuff. Is it a dynamic optimization? Then you need all of this stuff. So somebody needs to specify. Typically, you will sit with a senior engineer and you will specify what these requirements are. What is the model? What is the state space? What is the action space? And so on. Now let's go back to this example. I want to go to the space and then I want to come back to the launch pad. What is the state that you are going to pick? What do you think is a reasonable state in that particular situation? Location of the rocket is definitely a state, but you need slightly more than that.
Maybe velocity.
Sorry? Velocity. So yeah, of course, GPS position and velocity. What else is a state?
The rocket needs to be up, right?
Yeah. I mean, it doesn't go up like this, it goes like this.
Or maybe rotation of ECE.
So basically the relative position and relative velocity with respect to the launch pad, that's also an important state for the system. So that's why state is very important. It's important not just because you need to solve the problem, but it's also because the cost function the cost function needs to be influenced by the state. So all the variables that you think is important to specify the cost function or to specify the system model dynamics should be part of the state of the system. And then sometimes you need to, most of the time it's amply clear what the action is supposed to be. So these people will tell you, okay, these are the actions that you can take. And this is what the model is going to look like if you're maneuvering at high speed. So they'll take that as given, and that will be your UT. Anything else which has UT? So the landing gear will have its own controller, but they don't care about it. This one also people, they don't have to care about it. So I think UT is just influenced by the maneuvering at high speed part. So they will specify what UT is supposed to be. So then you will have XT, you will have UT, you will have the system model, you will have the constraints. Constraints would typically come from various physical constraints of the rocket, that it should not go above this speed, the thrusts are going to be of this particular magnitude. So all of those constraints will be specified by various components, people who are building different components of the rocket. So they'll specify what these constraints are going to be. Now you've collected all of this information. Hopefully there will be a lot of sensors around the rocket which is giving you this information. So you will have GPS sensors which will give you your state information. You will have attitude sensors which will tell you whether the rocket is like this, whether the rocket is like this. So those are attitude sensors. And then there will be some velocity sensors as well. There will be pitot tubes on the rocket which will tell you the airflow speed. So a lot of different sensors will give you the state information, so that you can evaluate this function, you can evaluate the constraint, and you can evaluate the terminal cost exactly at every point of time. Something that you need to worry about when you're designing these kind of dynamic optimization systems is if there is a communication failure. So you are expecting airspeed, airflow measurement to come to you in order to solve the optimization. But what if there is some ice that gets deposited in the airflow measurement sensor, and now it's not really measuring airflow? So how do you act in those situations? So you also have to think about failures. And if there are failures, then how do you handle those failures? So those are also important. So typically, that's why they will never have one sensor. They'll always have 5, 10, 15 sensors all over the place, so that even if one sensor fails, 2 sensors fail, your entire project is not going to fail. Okay? So they'll have that as a requirement as well. So now when all of this gets specified, so senior engineer and junior engineer and director of engineering, all of you guys will sit, you will decide on all of these things or all of these things, and then after that you will start writing the code for it. Okay, so writing the code part is actually very easy and straightforward, because we have all studied what that code is going to look like. You have solved some of those problems in your homework. Now, generally, the choice of an algorithm would come from the hardware limitations that you have. So if you have, so I don't know if you're aware, but when the Apollo mission was sent, the onboard computer had processing power that is much, much lower than the processing power of our cell phones today. Okay, so you can think of our cell phone powering an entire moon mission. That was the hardware at that time in 1969. And so if that is the hardware, what kind of algorithm would you use? Would you use dynamic programming? And the answer is no, we can't really use dynamic programming. So we have to use maximum principle. Now, even if you're using maximum principle, do you want to optimize over the entire 1.8 million time steps? Probably no. You want to only optimize 10, 15, 20 million, sorry, 10 or 15 or 20 time steps. And then after that, you will apply some sort of rollout method, or you will apply some sort of terminal cost from MPC, model predictive control. So hardware limitations will tell you what algorithm to pick. So because hardware limitations will tell you what the memory complexity should be and what the execution complexity should be, and how would you handle any failures in the subsystems that are giving you information, and how would you deal with failures in the downstream actuator control. So you have So, you know, in aircrafts, you have ailerons, you have tail, and so on. There are lots of control surfaces. And if one of the control surface fails, which typically happens, so engine failures could happen because the birds entered the engine and therefore the engine has failed. It's extinguished. So this has happened many times. I don't know how many of you have seen those failures. Otherwise, failures could happen because the actuator failures could happen because somebody bombed. Like there have been cases in World War II when one of the wing was bombed and the other wing is still surviving, and the plane kind of landed with just one wing, not the other wing. So those kind of things can also happen. So actuator failures can happen. Now in those cases, when a pilot is driving an airplane or piloting an airplane, then in that case, this entire thing is getting solved. The hardware is basically the brain of the pilot, right? But when you are creating autonomous systems, the hardware has real limitations. And so you need to figure out how to solve the problem with those hardware limitations. So, okay. Any questions so far? Okay. So let's talk about a specific problem, because this problem is on top of my head, so I'll talk about it. So we worked on a problem. So Ford came to us. Ford wanted us to solve the problem of scheduling EV charging over a 24-hour period. So the problem statement was clear. What was the CEO level problem? The problem was, we want electric vehicles to be charged with renewable energy, and we want to provide grid services. Okay, that was the problem, high level problem. Do we all agree that that's a good problem to solve? That's a problem, right? So we all agree that is a problem. We want electric vehicles to be charged with renewable energy. What are the different functional requirements and non-functional requirements? Well, without getting into the functional and non-functional side, the problem is renewable energy is stochastic, but we can have a forecast of renewable energy. So I know how much renewable, how much solar and how much wind energy will get produced tomorrow at 10 a.m., tomorrow at 10:15 a.m., tomorrow at 10:30 a.m., and so on and so forth. Okay, so that prediction, there are lots of companies that give you that prediction. So you give them a GPS location, and it will tell you exactly how much wind energy will get produced at that particular point, or how much solar energy will get produced at that particular GPS location. So we have the forecast, but the forecast is going to look something like this. So it's going to be cyclic in nature. And the second part is that the customer arrival and departure times are going to be stochastic, which means that you will come into the university, you have a 1 p.m. class, you might come here at 12 noon, or you might come here at 10 a.m., or you might come here at 8 a.m. So your arrival time is stochastic and your departure time is stochastic. Maybe some class got cancelled, and so you just want to go home, right? So that departure time is going to be stochastic as well. Now the problem is, we need to figure out how to charge all these electric vehicles that are parked on OSU campus. So do you know how many vehicles come to OSU campus every day? I don't know. I think maybe if I have a rough estimate, I think it will be like something like 20,000 vehicles would come to OSU every day. Okay, so they'll come, they'll park for a few hours, and then they'll leave. So some vehicles will come and park for 2 hours, some vehicles will come and park for 10 hours. Okay, some vehicles are university vehicles, so they are continuously parked. It's just that they park at different locations. Now assume that all of these vehicles are electric, and so now we need to figure out. We have this whole bunch of vehicles coming in, going out. We have this renewable energy system which is generating whatever it is generating, and now we need to match the supply to demand. And if there is a shortfall, we need to buy that shortfall from the grid. Now the problem is, so we need to be able to solve this optimization problem for tomorrow in order to figure out how should we be scheduling the vehicle. So the way we created this entire system was as follows. So the first thing that we figured out was so whenever you are parking the vehicle, you will enter how much energy you need, and until what time you are parked. So that way I will know two variables, which is your arrival time. This is your arrival time. Arrival time T, number of hours parked, M, and then amount of charge needed. This is going to be denoted by N. So I know your arrival time, I know how many hours you are going to be parked, and I know how much charge you need on a daily basis. So now 10,000 people are coming, or 15,000 people are coming, and they are giving you this information T, M, and N. Okay? How would you go about solving this problem? It's a dynamic problem, because at every point of time there will be different number of vehicles parked at the charging stations. So the question is, and we need to make the algorithm scalable. So one of the functional requirements was also that the algorithm should scale to 1 million vehicles, because eventually at the level of Ford, they are not looking at charging 10 or 20 vehicles. They are looking at charging 1 million electric vehicles. So whatever algorithm, whatever dynamic programming algorithm we should come up with, it should be scalable to 10 million vehicles, or 1 million vehicles. Do you know how many passenger cars are registered in the US, or passenger vehicles are registered in the US? Roughly 250 million, 250 to 300 million, right? So Ford might own, I don't know, 50 million of those vehicles. And so Ford needs to figure out if out of those 50 million vehicles, 10 million vehicles are electric vehicles, then Ford needs to figure out how to charge those 10 million Ford electric vehicles every day based on renewable energy production data of every day. Okay, so these are the three information that each person who is parked, each of those 10 million people will give us, and we need to figure out a way to solve this problem. So the way we solved the problem was, instead of figuring out the schedule for each electric vehicle, we categorized electric vehicle into vehicles with a similar arrival time, similar number of hours parked, and similar amounts of charge needed. Okay, so that way we are not looking at 10 million vehicles now. We are only looking at 150 categories of vehicles. Okay, so we took this information and we categorized into, say, 150 categories. And then we looked at how to charge individual categories of vehicles. So there was an aggregation scheme. So this is an aggregation scheme where we are aggregating all the vehicles into a category, into separate categories. And then there will be a disaggregation scheme at the end of the optimization process, where we will look at vehicles in each category and then figure out how to charge the vehicles in each category. So first, what we want to do is allocate the electricity generated to each category of vehicles. Okay, so we categorized, then it turns out that it's actually if you look at charging of categories of vehicles, then you can come up with a linear system model for this particular problem. And what are the constraints? So we could come up with the state space. The state space was very complicated, but basically it comprised of how many vehicles, what's the history of vehicles in category 1, history of vehicles in category 2, history of vehicles in category 3, and so on and so forth. So we stacked all of them together. We had a 1,000-dimensional state space. The action space was how much electricity you will be allocating to each of the categories. What do you think are the constraints on the system? What are the major constraints, functional and non-functional constraints on the system? So we want every vehicle to be charged by the time they are leaving. So they are coming at time t, they are going to stay at for m hours. So they are going to depart at t plus m. And I need to be able to deliver n megawatt of electricity or n kilowatt of electricity by the time t plus m is completed. So that's one constraint, that's a functional constraint. What other constraints do we have? We have charging rate constraint. So vehicles cannot charge completely in like 5 minutes. there is a charging rate and we need to maintain that charging rate. So that gave us another constraint. And the third constraint was because of the renewable energy production process. So if this is the confidence interval, so these are the two confidence intervals for renewable energy production, then I want to make sure that my total aggregate demand across all categories should be somewhere in between this. Okay, so this is the forecast. So maybe upper value of the forecast for renewables. This is the lower forecast, and this is the actual demand. So the actual demand must be between the upper value of the forecast and the lower value of the forecast for renewable supply. Okay, so these were the three constraints that we added into the system, and then we solved the problem. We came up with an approximate dynamic programming algorithm where neural network was our function approximator, and we only cared about value function. We didn't care about policy. So we got the value function by solving this problem using neural network as a function approximator, and it took us 3 hours to solve the problem for next day. Okay, so as you can see, 1 day worth of problem can be actually solved in like just 3 hours of time. And then the next day happens, and then we use a rollout algorithm to figure out how to actually allocate the charging process to individual categories of vehicles. And then once we figured out, okay, this much amount of charge should go to this category, then we figured out how to disaggregate and figure out a charging scheme for each individual vehicle within that category. So that's roughly how we solved the problem. The cool thing here was that you can scale it to as many vehicles as you want, as long as you don't change the number of categories. So number of categories is the main driver of computational complexity here, rather than the number of vehicles, because number of vehicles could be 1 million or 10 million or 20 million and so on. So Ford has come up with Ford Energy Rewards. It's a new program. If you like, I know many of you will go to California at some point of time, and then you will buy a Ford vehicle, and then Ford is going to call you and say, oh, please enroll in our Ford's Energy Rewards program, and we'll give you green electricity. Okay, that will be their pitch, and this is the algorithm that will hopefully be driving that whole green energy thing with Ford. So this is roughly what the process of solving an optimization problem is. You start with a business problem that everyone agrees on, that is the problem that needs to be solved. And so it percolates through the organizational process, and you come up with functional and non-functional requirements. Then somebody like you will need to sit down and translate it into the theory of optimization framework, so that you can start writing the algorithm, implement it on hardware, solve the problem, and hopefully create a lot of value for your company or your organization wherever you will be working. So any questions so far?
Why so many categories? Why not like 4?
4 will not work. You know, there are like different people will have different arrival time. So if you think about it, there are people arriving at 8 a.m., 8:15 a.m., 8:30 a.m.,
Okay.
8:45 a.m., and so on and so forth. So there are lots of different arrival times, lots of number of hours for which the vehicles will be parked. So each T, M, N tuple is a category.
Got it.
Okay, so if you have like 15 arrival times here and 5 different types of hours, like 2 hours, 4 hours, 6 hours, 8 hours, and 10 hours, and then 4 different types of amount of charge needed. So some vehicles will come at 80% charge, some will come at 60% charge, some will come at 40% charge. So you have like different requirements, as a result of which you will have large number of categories.
And then does it just interpolate into the right categories?
Kind of, yeah. When the vehicle arrives, you just put them in one category, and then you start the optimization process.
Okay.
Yeah, a lot of approximations. So you start with a very complicated CEO level problem that we want all electric vehicles to charge with renewable energy. So that's like a CEO level problem. And then you start doing a lot of approximations, and in the end you get a very nice optimization formulation that will hopefully get you closer to where the vision is. Yeah. Same thing will happen in medical image processing. I don't know, like there are people from all over the place. If you go to airlines, you will have similar issues. So it just, this thing will happen again and again, but overall, this is the flow of the process that you will notice in each of those problem statements that you will come across. Okay, so it was a lot of fun teaching you optimization. I've been teaching this course for a long time. So it's always amazing to teach an optimization class. Hopefully some of you will become faculty and you will teach optimization in your life. But that's pretty much it. The class has ended. I still have midterm 1 that I wanted to distribute, so I'll turn off the camera and then I'll distribute midterm 1 and midterm 2 papers. And thank you so much. Best of luck for your projects.